In my Structural Engineering Made Simple series, today I would like to talk about the moment axial load interaction data for reinforced concrete columns, also known as the MP diagram. Please take a moment and read the disclaimer at the bottom of this slide before we continue. The bending moment axial load interaction data provides information on the combined effect of the axial load and bending moment in representing the resistance of a column cross-section. The data is presented either graphically or in tabular form. If there is no bending moment applied on the cross-section, the axial load resistance is maximum. With the application of the bending moment, the axial load resistance reduces. This is to say that in fact the cross-section has a limited capacity that must be shared between the axial load and bending moment. In general, most square or rectangular sections have steel bars that are arranged around the perimeter of the cross-section. Therefore, in addition to layers of steel in extreme tension and compression areas of the cross-section, there are also layers of steel in between. This figure shows a cross-section of a column with 4 layers of steel, when considering the moment with respect to the x-axis axis. The compression side of the cross-section is on the right, and tension on the left of the axis x-axis, which passes through the centroid. However, if y-axis is considered, there will be 3 layers of steel. For the configuration shown and for the moment with respect to the x-axis axis, the 4 layers of steel are designated as follows. A'(1) is made up of 3 bars located at a distance d'1. A'(2) is made up of 2 bars located at a distance d'2. AS2 is made up of 2 bars located at a distance d2. And AS1 is made up of 3 bars located at a distance d1. Distances d1, d2, and d'1 and d'2 are measured with respect to the extreme concrete compressive fiber, which is on the right side of the section. When the cross-section is circular, the arrangement of bars is similar and is in many layers. For example, for the configuration shown, A'(1) is made up of 1 bar, A'(2) is made up of 2 bars, AS2 is made up of 2 bars, and AS1 is made up of 1 bar. Similarly, distances d1, d2, and d'1 and d'2 can be identified and measured with respect to the extreme compressive fiber. We will have an example coming up in this video showing how to compute these distances. These are the pertinent references used in the preparation of this video. Here are the notations. In addition to the designation for areas of steel and their locations, the strain and the stress in each steel layer is also designated with the same way. For example, as shown in this strain diagram. Epsilon prime S1 is a strain in A prime S1, and epsilon S1 is a strain in A S1, and so on. Also, F prime S1 is a stress in A prime S1, and F S1 is a stress in A S1, and so on. We also define the location of the neutral axis as x, which is also measured with respect to the extreme compressive fiber of the cross-section. By selecting x and knowing that the strain at the extreme compressive fiber in concrete is always equal to 0.003, we will then know the strain diagram across the cross-section. Procedure for developing interaction data. The procedure for constructing the interaction diagram for these sections is the same as the one we described in lesson 5 of this series. In that lesson, we talk about the simple case of having only AS and A prime sub S. However, in this case, we will have more than one layer of steel in each of the compression and tension sides. The strain diagram will help us compute the stresses at these steel layers. Thus, before we start selecting various strain diagrams and computing the corresponding Pn and Mn, we must identify the number of bars for each steel layer and the distance of each steel layer from the extreme compressive fiber of the cross section. Notice that the subscript n is used to indicate that Pn and Mn are the nominal axial load and bending moment resistances. Then we follow the following steps to generate a sufficient number of points to plot the interaction diagram or show the data in a table. Step 1. Compute the maximum axial load capacity Pn0. This corresponds to the case where Mn is equal to 0. Pn0 is equal to 0.85 prime sub c times Ag minus Ast plus Fy times Ast. In this equation, F prime sub c is the compressive strength of concrete, Ag is the gross area of the cross section, Ast is the total area of steel, and Fy is the yield strength of steel. Step 2. Select different values for x, establish the strain diagram, and compute the stress values at each steel layer. It is a good idea to start with the strain diagram for the balance condition for which x is equal to xp as follows. xp is equal to 87,000 divided by 87,000 plus Fi, the quantity multiplied by dt, which can approximately be taken as 0.6 dt. And dt is equal to d1, and we use pounds and inches in these values for this equation. Now recall that the strain diagram corresponding to balance condition has 0.003 at the extreme compressive fiber on concrete and exactly a strain equal to epsilon y at the very first layer of tension steel. Then select a few cases with x larger than xp and a few with x smaller than xp. Step 3. Compute the stresses Fs1, Fs2, etc. and F'(1), F'(2), etc. from the following equations. These equations are given in generic form. They are designated by the subscript I. Fsi is equal to 87,000 times di minus x divided by x, and the absolute value of this quantity cannot exceed Fy. Again, we are using pounds and inches. F prime Si is equal to 87,000 times x minus d prime I divided by x. And again, the absolute value cannot exceed Fy. And the subscript I is equal to 1, 2, etc. Note that for the balance condition and also for all cases of the strain diagram where x is smaller than xp, Fs1 is always equal to Fy. Also, if Fs1 and Fs2, etc. become negative, it means they are actually under compression. Step 4. Write the equations of equilibrium for the internal forces to compute Pn and Mn. The free body diagram of internal forces for a sample strain diagram for a rectangular section and a circular section are shown in the next slide. Notice that the eccentricity E is always equal to Mn divided by Pn. The upper figure here shows the cross-section detail. The lower figure shows a longitudinal detail with internal forces at the cross-section shown. Note that for this strain diagram, AS2 is also under tension. However, there are many cases where it will be under compression. Also note the compression stress on concrete is 0.85 prime sub c, and extends over the distance a, where a is equal to beta 1x, beta 1 is equal to 0.85 for prime sub c equal to 4000 psi or smaller. For every 1000 psi, when a prime sub s is more than 4000 psi, beta 1 is reduced by 0.05, with the smallest possible value for beta 1 equal to 0.65. Also notice the forces in the compression and tension still shown in the diagram. Here is a circular section. Again, the upper figure shows the cross-section detail. The lower figure shows the longitudinal detail with internal forces at the cross-section. Note that the longitudinal detail and forces shown are very similar to the case of a rectangular section. And again, A is equal to beta 1x. And the strain diagram is identical to the previous case. Equations for Pn and Mn for a rectangular section. These equations are for a case of x larger than xp. Pn and Mn are given based on the equilibrium of forces as shown to the right. Notice that if Fs1, Fs2, Fs3 become negative, it means they are actually under compression. Therefore, we use negative values for these stresses in the above equations. More accurate values for Mn and Pn are found when the effect of displaced concrete in compression area because of placement of compression steels is considered. To consider this effect, F prime S1 minus 0.85 F prime sub C is used instead of F prime S1 and so on. Rectangular section continued. For cases with x smaller or equal to xp, the Pn and Mn equations are given, which are slightly different from the previous equations. And notice that in these equations, Fs1 is always equal to Fy. And again, if Fs2 and Fs3 become negative, it means they are actually under compression. So we use negative values for these stresses in the above equations. This would actually happen if D2, D3, etc. are less than x. Equations for Pn and Mn for a circular section. For cases with x larger than xp, the two equations are given. Again, very similar to previous equations, except that you notice two new parameters a sub c and y bar appear in these equations. A sub c and y bar are the area and location of the center of a sector of the cross-section which is under compression. Equations for computing these parameters are given in the next slide. Again, notice that if Fs1, Fs2, Fs3 become negative, it means they are actually under compression. Thus, use negative values for these stresses in the above equations. And again, in here, the eccentricity is equal to Mn divided by Pn. The equations for computing A sub c and y bar are given in here. Shaded areas show compression area where 0.85 F prime sub c applies on the section. The shaded area is A sub c. The upper figure shows when A is smaller than h over 2, while the lower figure shows when A is larger than h over 2. Let R be equal to radius of the cross section, which is h over 2, then cosine alpha, the angle alpha is shown, can be found as R minus A divided by R. Then the area A sub c and y bar can be computed based on the two equations given. A point of caution, you must use radians in these equations. If you use degrees, you end up with wrong results. Circular section continued. For cases with x smaller than xp, the equations Pn and Mn are given based on the equilibrium of forces shown to the right. And these equations are slightly different. And in these equations now we notice that Fs1 is always equal to Fy. And we emphasize that if Fs2 and Fs3 become negative, it means they are actually under compression, so we use negative values for these stresses in the above equations. This would happen if D2 and D3, etc. are less than X. For circular sections, distances d1, d2, d'1, d'2, etc. can be found from the geometry. For example, if 6 number 8 bars are used with a protection cover of 1.5 inches and a number 4 tie or a spiral and h equal to 18 inches, we compute d'1 as 2.5 inches, where that 4 over 8 is actually the diameter of the tie and 1 is the diameter of a number 8 bar. Here we show r' as the radius of a circle passing through the center of longitudinal bars. This is shown in the lower figure. Knowing this r' and the angle beta, we can find out the distance d'2. Angle beta for a 6-bar arrangement is equal to 60 degrees. R' is equal to, therefore, 9 minus 2.5, which is 6.5 inches, and d'2 obtained as R' times 1 minus cosine beta plus d'1. The answer is 5.75 inches. By using d'1 and d'2, we can easily find d2 and d1, and these are equal to 12.25 inches and 15.5 inches respectively. Here is an example. In this example, we have a square section with the configuration shown. F prime sub c is 4,000 and Fy is 60,000 psi. The size of this square section is 16 by 16 inches. 8 number 9 bars are used and number 4 ties are used. Area of number 9 is 1 square inch and its diameter is 1.128 inches. The protection cover is 1.5 inches. We only have 3 layers of a seal as follows. A prime S1 is made of 3 number 9, so the area is 3 square inches, and D'1 is obtained as 2.56 inches. AS2 is located right at the middle, therefore D2 is 8 inches, and there are 2 bars in that layer, so the area is 2 square inches. And finally, AS1 is made up of 3 bars, therefore the area is 3 square inches, and the distance D1 is 16 minus 2.56, which is 13.44 inches. Now we consider the balance condition. XB for the balance condition is equal to 0.592 D1. It is equal to 7.95 inches. And therefore A is equal to 6.76 inches. And notice that the middle layer is under a tension force because D2 was larger than X. We find the stresses Fs2 and F'S1 using the equations given previously. Once we find these stresses, make sure to check them against the upper values of 60,000 psi. The absolute value of these stresses cannot exceed 60,000 psi. For Fs2, we find a very small amount, 547 psi, and for F'S1, we find 58,985 psi. And notice that Fs2 is under tension, F'S1 is compression. The pertinent equations for Pn and Mn are given with the corresponding values computed by plugging those numbers into the equations. The Pn is equal to 363.6 kips and Mn is equal to 3,640.8 inch kips. And of course, the eccentricity is now about 10 inches, dividing Mn by Pn. Now we can pick up any value for x and generate more points or more data for our interaction data. For example, if we select x equal to 6.72 with a being equal to 5.71, and again noticing that d2 is larger than x, therefore the middle layer would be under tension, we can find the stresses paying attention to now Fs1 is equal to Fy, which is 60,000 psi, and Fs2 and F'S1 computed accordingly. And once we plug them in the equations for Pn and Mn, we find Pn equal to 259 kips and Mn equal to 3456.3 inch kips, with the eccentricity equal to 13.3 inches. We have also tried x equal to 12, 11, 10, and 9 inches. The values for Pn and Mn are listed in this table. Notice that Pn0 is also computed. The value is 1323.2 kips, and that corresponds to a case of x equal to infinity, theoretically. And here is a graph, the interaction diagram, Pn versus Mn. Resistance reduction factor. Sometimes the interaction diagram is plotted in terms of phi Pn versus phi Mn, where phi is the resistance reduction factor. To compute phi, similar to a beam design, the strain epsilon t at the very first layer in the tension side is needed, which is equal to 0.003 times dt minus x divided by x, noticing that dt is equal to d1. This strain value is used in computing the resistance reduction factor. For a tight column, phi is equal to 0.65 as the smallest value and goes to a higher value of 0.9. For strain values between 0.002 and 0.005, we use a transitional equation, the middle. And for a spiral column, phi is equal to 0.75 as a minimum, and the transition equation is again given at the middle. Furthermore, the ACI has upper limits for the axial load capacity. Thus, the phi Pn, phi Mn diagram will look different. These are the upper values for the axial load capacity. 0.85 Pn0 for tight columns, 0.85 phi Pn0 for a spiral column. The graph to the left is a Pn-Mn diagram, which is also called the nominal diagram. The one to the right is a phi Pn phi Mn diagram, which is also called the design diagram. Notice that the lower portion of the diagram is a little bit distorted. This is because around those areas, phi is now increasing to almost 0.9. In this example, we now consider a circular spiral column. We want to develop the phi Pn phi Mn diagram. The column has a cross section with 24 inches of diameter. Reinforcement is made of 8 number 10 bars. A spiral is a number 4 bar. Protection cover 1.5 inches. Furthermore, if Prime sub c is 4,000, Fy is equal to 60,000 psi. The interaction diagram is developed based on selecting different locations for the neutral axis. Distance of the neutral axis from the extreme compressive fiber is taken as x, and then computing Mn and Pn. The capacity reduction factor phi is then computed based on the strain epsilon t and applied to Pn and Mn. Please note that there are 5 layers. Numbering for layers starts from the right and continues to the left. Layer 1 and 5 each is made up of 1 bar only. All other layers have each 2 bars. Based on the geometry of a system and the bar arrangement, the following values are computed for bars. Layer 1, A prime S1 is equal to 1.27 square inches, and D prime 1 is computed as 2.64 inches. Using the equations given before, we can find out D prime 2, which is 5.38 inches, and the area A prime S2 is 2.54 square inches, and so on with the other layers. For the balance condition, XB is equal to 12.65 inches and A is equal to 10.75 inches. Using the equation given before, for computing a sub c and y bar, we compute these parameters. Notice that radius r is equal to 12 inches, that's h over 2, and based on that we find cosine alpha. Alpha is equal to 84 degrees, but remember that we must use radians. So alpha is equal to 1.466 radians. Therefore, a sub c turns out to be equal to 196.3 square inches, and y bar is equal to 6.226 inches. Now we find the stresses in different layers of steel. F prime is 1 and Fs1 each is equal to 60,000 psi. However, one is in compression, another one is in tension. And F prime is 2 is 50,008 psi in compression. F prime is 3 is 4,457 psi in compression. And Fs2 is 41,093 psi in tension. Using the equations for Pn and Mn given earlier, we find that Pn is equal to 701.3 kips, Mn is equal to 567.7 foot kips, and the eccentricity, which is now corresponding to balance condition, is equal to 0.81 feet or 9.7 inches. For the balance condition, phi is equal to 0.75 for the spiral column. Therefore, phi Pn and phi Mn can be computed. We are 526 kips and 425.8 foot kips respectively. Using other values for x, we continue with computing several other values for Pn and Mn. Also for values of x smaller than xp, the resistance reduction factor phi slowly increases from 0.75 to 0.9 based on the values of a strain epsilon t. The table on the next slide shows a summary of the values of x, Pn, Mn, and E, values of epsilon t, values of phi, and finally phi Pn and phi Mn. Here is a summary table. Please notice that the balance condition is shown with red, and if you look at the first column, the Pn0 computed as 2113.2, and you look at the last row, you notice that Pn is equal to 0, and that is pretty much corresponding to a case of pure bending moment, with the eccentricity is approaching infinity. And here are the graphs. The upper graph shows Pn versus Mn. The lower graph shows phi Pn versus phi Mn, with the upper portion of the curve is cut because the ACI has that maximum value for the axial load capacity. The interaction data is useful in the analysis and design of reinforced concrete columns. In practice, often a cluster of diagrams for the same cross-section but different steel arrangement is shown and is used as a design aid. Thank you for watching this video.